Hello, I'm Chris Mack, your instructor for the Data2Decision class, and this time I'm going to demonstrate some capabilities of doing linear regression in Excel. Excel is one of those tools that almost all scientists and engineers have access to very, very easily, and so we tend to use it for a lot of simple data analysis tasks. I use it very frequently, and only when I need something beyond the normal scope of what Excel can do I move on to something more sophisticated like R. But we're going to use Excel a lot in this class, so I wanted to demonstrate some of the different ways that you can do a linear regression in Excel. In particular, we'll do a simple straight line fit set of data using ordinary least squares regression. And in fact, there's 5 different ways that you can do that in Excel with varying degrees of ease of use and capability. Let's begin with the simplest one, and that's to add a trend line. So here I have a set of data. There's the trials, the X just numbered. There's the X values and the Y values. And I created a graph of those X and Y values here. Now I already have the trend line set, so there if I double click on it I get the properties of the trend line, but I'm going to delete that trend line so that we can start from scratch. So now I have a graph of the data. If I right click on a data set, select add trend line, I have the options. I'm going to pick a linear trend line, and I'm going to display the equation on the chart and display the R squared value. When I do that, I see exactly what I'm hoping to get, the equation of the line, intercept, and the R squared. Alternately, we can use the built-in functions slope, intercept, and RSQ. They're shown here. So here is the slope function. Pick the Y values first, then C9 through C19 here, then the X values, B9 through B19, and that slope function tells me the slope value. The intercept function tells me the intercept value, and the R squared, RSQ, R squared function, squared. Now what we don't get from any of this is the standard errors in the slope and the intercept, other important information that we need. So this is a very limited way of doing linear regression. We can also do these calculations by hand. So we have seen in the class some of these formulas, which I've cut and pasted into this Excel spreadsheet so that you can see them all in one handy reference. The slope and the intercepts, but also the standard error of the residuals, the standard error of the slope squared, and the standard error of the intercept squared. We take the square root of those and we have our standard errors which we need. So again, I have the same data in X and Y. To perform this summation, I need to first calculate the mean value of X. Then I need to subtract off the mean from the X values and the mean value of Y from the Y values and sum up the squares of those and the products of those and take the division of those and we get the slope. So first, I subtract off the mean. So this is the X minus its mean. So I put down here at the bottom a sum and a mean column, average of all the X values, and here's the average of all the Y values. So if I subtract off the average of all the X values, oops, cancel, I get the X minus the mean row, and I sum all them up. Here's the X minus mean quantity squared. So you see I put a squared value there. So calculate those and sum them all up. Here's the Y values minus the means. And then in this column, I take the X minus its mean, multiply it by the Y minus its mean, and I sum all them up. Now once I've got all of those pieces, I can calculate the slope. So up here is the formula for the slope, just simply the sum of all the X means minus the Y means. You can see I misspelled mean here. Change that real quick. There we go. X minus its mean and Y minus mean, there's the sum of all those. So I take that number and divide by E20, which is X minus its mean quantity squared, all those summed up. And there's my slope. And you see I get the exact same number that I got when I use the built-in Excel function of adding a trend line. Similarly, I apply the formula for the intercept, but I can also calculate the residual standard errors. Square root the sum of the squared residuals divided by the degrees of freedom. So this is an important point I want to mention. If you by hand calculate the residual standard error, the standard deviation of the residuals, you have to use the number of degrees of freedom, which is the number of data points minus the number of parameters. We have 11 data points here. We have 2 parameters, a slope and an intercept. And that takes away 2 degrees of freedom, so we only have 9 degrees of freedom. I calculate the residual as the difference between the actual y value, C9, and the equation, which is intercept plus slope times x value. So I subtract off the equation value, predicted value, the model value, and that becomes my residual. There's the residual squared, and here's the sum of all the residuals squared. So that's the SSE, the sum of the square errors, which is actually the thing that's minimized by applying all these equations. So now I take this number, divide by 9, number of degrees of freedom, and take the square root of all of that, and I've got the residual standard error. And I can calculate the standard error of the slope and the standard error of the intercept by applying these equations. So we can do this stuff by hand. It's kind of course, difficult programming all these equations, etc., etc. Excel has built-in functions to do this for you, and the most valuable built-in function to do this is called Linest. Linest is my linear estimator for linear regression. So again, I have the exact same data. I show a plot of that data, and I show the best fit line using the trendline function. But what I'm going to do now is use the Linest function. Now, it's shown here as Linest, etc. It's called an array function, and an array function requires some interesting things to make it work. And if you're not used to using array functions in Excel, it's a little bit kludgy. But nonetheless, get used to it pretty quickly. I cut and paste right here some information from the help file, the Excel help file, to remind me of how to deal with the Linest function and the array capabilities of that. Because I always forget. And after a few months of not having done it, I'll forget the exact, F2, Control Shift Enter magic keystrokes. So I just cut and paste it there. Every time I need to use Linest, I always go and find this from a different spreadsheet, cut and paste it, so I always have it there ready for me. So what I'm going to do is delete this Linest results, start from scratch. So I go up to the corner of where I'm going to put all my results. I do equal Linest. All right, it says now known y's. And so I select the array of all the y's. Then comma, input the known x's. Select all those. Comma, constant. The intercept. If I want to set the intercept to 0, I put false here. If I want the intercept to be calculated, I put true. So I'm going to type true. And then the last parameter, do I want all the regression statistics or just the slope? Well, why would you do Linest if you didn't want everything? So true, yes, we want all, except for you got to spell it right. True, we want all the statistics. So do that, and I hit enter. And there's a number. One number. What I have there is the first number that comes out in the array of outputs, and it is the slope. I want everything. So what do? I have to use this little trick that I've got described here. Select 2 columns and 5 rows, starting with the formula cell. So 2 columns. I'm holding down Shift and using my arrow keys. 5 rows. So I have that all selected. Now it says press F2. There's my F2. Then press Control Shift Enter. When you do that, it fills in that array with all of the results. What are the results? Again, using the Excel help function, I have cut and paste a legend. that tells me what all of these numbers are. Here's the legend right here. So the first ones are B1 and B0, that is the slope and the intercept. The next two are the standard error of the slope and the standard error of the intercept. Those are the critical things that we need, and that's why we're using Linest instead of just a trend line. So the standard error of the slope, if I square that, that's the variance of the slope. I'll be using this when calculating confidence intervals. Then I have R squared, the R squared value, which of course matches the R squared value here from the trend line. Then I have the standard error of the residuals, or the standard error of the Y value, SEY, standard error Y. Standard error of the residuals and the standard error of the Y values are the same thing. Because there's no uncertainty in the model, all the uncertainty in the Y becomes the uncertainty in the residuals. So you note that if I go back, that number, 1.236603, if I go back to my by hand calculation, there it is, same number. It's because I divided by 9 the number of degrees of freedom. That's what Linest does too. In fact, Linest tells me the number of degrees of freedom. It's 9. We have another statistics, the F statistic, which we'll use later in doing some hypothesis testing about the goodness of the model. We won't talk about that now. So that's basically the statistics that we need and we're going to use. And Linest gives it all to us. Linest can do more than just a single input variable, a single predictor variable. You can have any number of predictor variables, and that's another one of the good things about Linest. You can use it for multiple regression, where you have more than one predictor variable. Now, Excel has even more capabilities. It has the ANOVA capability. ANOVA is something that's available in the analysis tool pack. So if you haven't installed the analysis tool pack in Excel, you'll want to do that. You need to go look up in the help or search online for how to install the analysis tool pack. It's relatively simple. I won't explain how to do it, though. You can find that out yourself. Then once you've got it, you've got this data tab set, and you've got a data analysis button, which when I select it, gives me a whole bunch of different data analysis options. Random number generator, histograms, we'll use histograms later, descriptive statistics, and ANOVA. Or regression. And it's regression that we're going to use, the ANOVA regression. So if I select regression and hit OK, you input the Y range and the X range. So the Y range is here, and the X range is here. Now, if I had multiple X variables, X1 and X2 and X3, multiple regressors, I could select more than one column, and that would be a multiple regression. All right? Now, output range. Once I've set the inputs, I have some options available to me. I'll select the output range, and what I'm going to do is simply select the cell where I want the outputs to begin. So I'll select there, and it will dump all the stuff starting there. And if I want residuals or standardized residuals or residual plots or line plots or normal probability plots, I can select those. Let me just select them all just so you can see what's there. Yeah. As soon as I hit OK, it's going to ask me if I want to, it's okay to overwrite the stuff that's already there. I'll say OK. And there it is. It just dumped all this stuff. I had to put up a few graphs. I already had the graphs there, so it added some new versions of the same graphs. I'll go ahead and delete because it just piled the new graph on top of the old graphs that I already had. And there we go. We now have all of these statistics. What are the statistics? Well, it's got the R square. Got something called an adjusted R square, which we'll learn about later. It's got that same standard error of the residuals, exact same number we've seen before. It tells me this is called the ANOVA table. We'll see some ANOVA table stuff in the future, but there are 9 degrees of freedom in calculating the residuals, as we've seen before, residual standard error. Here's the main stuff we need: the intercept and the coefficient of x variable 1, which is our slope, and the standard errors of those quantities. Notice that it also calculates the t-statistic for a 95% confidence interval and the p-value associated with that. The confidence intervals, lower and upper 95% confidence intervals, are also calculated for both of those. So that's very, very handy if you want a 95% confidence interval. I'm going to make you, in this class, do some of those calculations by hand, given the standard errors. It has the residuals, the predicted y values, the residuals, standardized residuals. We'll talk more about there. And it does what's called a normal probability plot, or a QQ plot. We're going to learn about that in a coming lecture, 1 or 2 lectures away from now. So this regression approach is pretty valuable with lots of good information. Most of the information is in Linest as well, so not a whole lot new, but formatted a little bit differently and a little bit extra information. Finally, the last way, not the way I recommend, but the last way you can do regression in Excel is you can use Excel's matrix math capabilities. Matrix math Excel is not very user-friendly. Nonetheless, you could set up matrices and do multiplications and apply all these formulas. So I cut and paste all these formulas from the lectures and stuck them in here, and our design matrix and our equations for solutions. Here's the data set. I can set up matrices corresponding to x and y and calculate residuals and calculate b hat and the covariance matrix and everything. I'm not going to go through all the details of that. It's all here, and it uses things like mult, matrix multiplication. Notice that it is an array calculation. So you type in the formula, and you have to go over the area. So you have to know the size of the matrix that will come out of your multiplication. You do the F2, Control-Shift-Enter, just like we saw before, etc. Kind of a pain, but, well, if you're interested in learning about how to do this matrix math, Excel forces you to kind of set it up manually, and that's good, actually, the first time you do it anyways. Not so good if you're going to do it over and over again. So here's a list of some of these functions that I've used, and if you want to, totally optional, you can see how all these are calculated. Notice that one thing I can get out of this is the hat matrix. That's something that the other Linest and ANOVA don't give me. The hat matrix and the both diagonal and cross elements of the hat matrix are very valuable information to know. In Excel, we'll generally only be able to get that using something like this matrix approach. And that's why we're going to rely mostly on other more sophisticated statistical analysis software to get us that useful information, things like the hat matrix. All right, there's 5 different ways of doing straight line linear regression in Excel. We will have a 6th way using the real statistics package add-on later on in the semester. That's it for this demo. Thank you very much.